Another day, another story. Pour one out for old space and time. In the vast cosmic theater, a theoretical physicist has embarked on a journey through the eons, using iron's signature qualities to trace forward to the end of the universe, guided by the spectacular deaths of stars. Meet Matt Caplan, a computer-aided cosmologist, who calls his field of study astromaterials. These are the impossibly dense remnants left behind by dying stars, stellar matter that contracts to the extreme, freezing solid. Caplan, who teaches and researches at Illinois State University, relies on advanced simulations to explore these cosmic enigmas. In this groundbreaking research, Caplan peers into the future of the universe, a time when star formation has long ceased. What he finds is a universe populated by sparse, degenerate remnants, primarily white dwarfs. But their ultimate fate remains a tantalizing question mark. Caplan elucidates, these white dwarfs will cool and freeze solid into black dwarfs, while a curious process called PYCNONU clear fusion will gradually transform their composition into iron-56. PYCNO, meaning thick, nuclear fusion is triggered by the astonishing density of these remnants. Unlike thermonuclear reactions, where heat is the catalyst, it's the sheer density that sets off this extraordinary reaction. As iron accumulates, the rest of the star fades away, and iron takes over, extinguishing the other elements. Iron is the cosmic spark that ignites a supernova, but smaller stars lack the necessary catalytic iron. It's the massive stars that explode into supernovae, fueled by their rich iron content. According to Caplan, most of the supernovae we witness today are the explosive endgames of these massive stars. But smaller stars, with their slower iron accumulation and fusion reactions, remain dormant, biding their time. In the dark recesses of the universe's twilight years, the last remnants, the long-simmering white dwarfs, will rekindle like trick birthday candles. Finally, their centers will achieve the density and ferrous richness needed to trigger their own cosmic fireworks. Caplan elaborates, as white dwarfs cool down over the next few trillion years, they'll grow dimmer, eventually freeze solid, and become black dwarf stars that no longer shine. Caplan's simulations are not only measuring the iron's accumulation rate in these stars but also pinpointing the critical juncture where iron leads to the timely demise of stars of various sizes. The grand finale, the smallest trick candle, supernovae, will occur about 10 to the power of 32,000 years into the future, somewhere between a Google and a Googleplex. By then, galaxies will have dispersed, black holes will have evaporated, and the universe's relentless expansion will have driven all objects so far apart that even the faintest glimmers will remain forever unseen. Caplan somberly concludes, it won't even be physically possible for light to travel that far. The last stars will fall, like the proverbial tree in a forest, with no one around to hear the sound, not even other stars. So, as we contemplate the cosmic finale, we're reminded that in the end, the universe's swan song will play out in silence, in a realm where time itself bows to the laws of entropy, and all that remains are the echoes of a bygone era. Thanks for watching.